Problem 77. I would say this problem is a little bit challenging too, so it takes a little bit time to solve this. So I would suggest to spend at least 30 minutes. Try your best to solve this problem before seeing the rest of the video. And also, I'm not gonna go to all the details of it, but I'm gonna give you some hints how to solve it. So in this problem, we have this crank, which is rotating with angular velocity of omega 0, which is 4.5 radian per second, and it is constant. We have this bar, which has this roller at this end of it, which is on the ground. And the question is, what is the force between this roller and ground? That's our objective. So if I want to draw the free body diagram of this AB, so let's say this is AB. From joint A, because we have a pin here, it is possible to have force in two directions, right? In AX direction, AY direction. And also from this roller, it is possible to have a force in the vertical direction. Let's call it B. And of course, we have gravitational force on AB as well, mg. Okay. One of the methods you can use here is using D'Alembert method. You have different options, but D'Alembert is usually very helpful. Which means I need to find the acceleration of the centroid and add another force here, an imaginary force, with the magnitude of mass times negative acceleration. And also I need to find alpha, angular acceleration of this rod, and add a moment with the magnitude of I about the center times negative alpha. Then everything is gonna be, then the problem is gonna be a static problem. You can say some of the forces in any direction is equal to 0, and some of the moments about any point is equal to 0. So analyzing the kinematics of this, we had it in chapter 5 as well. So I'm not gonna go to the details of it, but by writing the relative velocity equation between A and B, or finding the instantaneous center of rotation of AB, you should be able to find omega of this bar. And if you do correctly, omega is going to be equal to 3 radians per second in clockwise direction. So I'm gonna let you do that part, but omega of AB should be 3 radians per second in clockwise direction. Again, to find it, you can use instantaneous center of rotation or relative velocity equation between A and B, which is quite easy. We had a lot of similar problems in chapter 5. And also, by writing the relative acceleration equation between A and B, you're going to be able to find acceleration of B, which is not really useful here, but importantly, you're going to find alpha of AB. And alpha of AB, if you do it right, is going to be 12 radian per second square. Radian per second square in counterclockwise direction. So after finding omega and alpha, now we can find the acceleration of the centroid. Let's call it g. What is the acceleration of the centroid? Acceleration of the centroid is equal to acceleration of A plus acceleration of g with respect to A, which has two components if you remember from chapter 5. One component is omega squared times negative r, which is GA, right? So omega squared times GA, and also alpha times AG in this direction. So acceleration of g if I want to write here, it's gonna have, we need to combine three things together. Acceleration of A. By the way, what is the acceleration of A? We need actually to know that too. Acceleration of A is gonna be r omega squared, omega 0 squared toward O. And A is not gonna have tangential acceleration because omega 0 is constant. So acceleration of A, if I write it here, is 0.4 times omega 0 squared to the left in this direction. So acceleration of G is gonna be acceleration of A in this direction plus GA times omega squared toward A. So it's gonna be 0.5 from G to A is 0.5. 0.5 times omega of AB squared, and also alpha cross R in that equation. So it's going to be perpendicular to this, and because alpha is in counterclockwise direction, the tangential component of acceleration of G with respect to A is going to be 0.5 times alpha of AB. So by combining these three together, we can find acceleration of the centroid. Okay. So what we should do here in the free body diagram to use D'Alembert method, I need to multiply mass to the negative of these accelerations and put them here. Then I'm gonna have a static problem. So I have this acceleration, so negative of it, I need to multiply the mass of AB, m times 0.4 times omega 0 squared. Mass times negative of this is going to be force in this direction, so it's going to be 0.5 times mass times omega AB squared, and opposite of this times mass is going to be 0.5 times mass times alpha of AB squared. And also we need to add a moment too, a moment opposite to alpha, because alpha is clockwise. I'm going to add a moment here with the magnitude of IG times alpha of AB. So doing all of these steps takes a little bit time to do. But at the end, we have a static problem here because of the D'Alembert principle. So I can say some of the forces in any direction is equal to 0, some of the moments about any point is equal to 0 too. My objective here is finding B. If you look at this free body diagram, I don't know what is AX, I don't know what is AY, I don't know what is B. By kinematic analysis, I found omega and alpha, so I know all of these forces, right? All of them are known. So if I want to find only B, the easiest method is taking moment about point A. So sum of the moments about point A is equal to 0. So moment of B is going to be B times perpendicular distance from here to here, right? Then mg times perpendicular distance of it, then same thing for this one, same thing for that one. And this one is not going to make any moment. Moment of ax and ay are 0, so they're going to cancel out from the equation. And also we have this ig times alpha ab as well. So we need to add that too in clockwise direction. So I'll let you do that. So in that equation, you are going to have only one unknown, which is b. So we should be able to find b from this equation. And b is going to be 36.4 Newton. So I didn't give you all the details, so you have something to do. But I explain what is the procedure to solve this problem.